Let's assume that f is defined on AB and goes on to R0 plus. That means the strictly positive numbers, real numbers. It's continuous on AB and differentiable on AB, not including the boundaries. We want to show that there exists some C in AB such that f of b over f of a is the exponential of f prime of c over f of c times b minus a. This problem is requiring the mean value theorem for derivatives. And we see here that these are the conditions that we need to apply the mean value theorem. But to apply the mean value theorem, we need to change this function here. Okay, because the mean value theorem states that under these conditions, there is a C such that f prime of c is f of b minus f of a over b minus a. Okay, and here if we can see, I think I spilled some coffee. Okay, that's fine. Here we see that we have f prime of c over f of c. This tells us that we need to change our function here. So we have f defined from on AB and going on to R plus and R plus excluding the 0. Here, if we extend this function to some, we extend this one. If we define here the log, okay, we're gonna have a function, another function that we can define. So if we define this one here, define the natural log of f. So if we define g, okay, let's define it. In fact, that's what we're gonna do. If we define g of t as the natural log of f of t, okay, we will have the following. Okay, we will have g of t is defined on AB and going onto R. And this is the composite of two continuous function. Therefore, g of t is continuous and differentiable on AB. And therefore, this tells us that we can apply the mean value theorem for g of t. Okay, so doing so, we know that in this case, there exists some c. There is a c in the interval AB such that g of b minus g of a over b minus a is g prime of c. All we need now is to translate these quantities into this one. Okay, we have g of b is the natural log of f of b minus the natural log of f of a over b minus a. And g prime of c, we know the derivative now of g prime of g because this is defined in function of the log. So in this case, we know that this is just f prime of c over g over f of c. Sorry, not g of c, f of c. Remember that the composite using the chain rule, the derivative of u, some function, is going to be u prime over u. And here we have u is f. So we have f prime of c over f of c. F prime of c over f of c. Okay, here using the laws of the log, we can have the natural log of f of b over f of a. And we can multiply b minus a into this one, b minus a times f prime of c over f of c. Okay, to get the result that we need, we take the exponential of both sides. Okay, so we take the exponential, we have f of b over f of a is the exponential of f prime of c over f of c times b minus a. And this is what we need. This is what we need, and this is just a simple application of the mean value theorem, but we have to change the function here to get this form, because we are used to this form here. So changing it here and using the fact that the natural log is defined on 0 infinity, not including the 0, we get the result. And using the fact that the composite of two continuous function is continuous, the composite of two differential function is differentiable. And applying this condition here, we know that this c exists in this interval, and using this ratio, we have the result. Remember that the mean value theorem says if you have your function defined on some AB, continuous and differentiable, not including the bounds, if you have your function like this, then there is some c here in AB, such that the slope of f at c is equal to the slope of the line, the secant line, going through the points a f of a and b f of b. So we see here clearly, we see that this one here, the c on the curve and the c on the secant line, they have the same slope. Okay, this is great theorem, and one needs to know this one, and you need to know how to apply it. It's very useful. It's one of the fundamentals of mathematical analysis. Great theorem, and one needs to know this. Okay, if you see any errors or mistakes, please comment, share, and subscribe. Thank you very much.